Ever wondered how those beautiful snowflakes form with their intricate designs? Well, the answer lies in one word: crystallization. It is the process where solid crystals spring to life from a homogeneous solution. Think of it as a magic trick where the unseen suddenly becomes seen in the most spectacular way possible. Now you might be wondering, why is crystallization so important? It's because this process plays a vital role in numerous fields. In chemistry, it's used to purify substances. In geology, it explains how rocks and minerals form over time. In material science, it helps in the development of new materials. It's like the unsung hero behind the scenes, making things possible without us even realizing it. So, as you can see, crystallization is more than just about pretty snowflakes. It's a fascinating process with wide-ranging implications. Now let's dive deeper into the science behind crystallization. Ever heard of Miers' theory of supersaturation? Let's dissect it. This theory revolves around the concept of supersaturation, an intriguing state of a solution that contains more of the dissolved material than it would under normal conditions. Imagine a cup of tea that can miraculously hold 10 teaspoons of sugar instead of the usual 1 or 2. That's supersaturation for you. But how does this happen? The key lies in manipulating conditions such as temperature and pressure to coax the solution into holding more solute than it typically would. When these conditions are returned to normal, the solution remains supersaturated, brimming with an excess of solute. Now, supersaturation isn't just a fun party trick. It's a critical player in the world of crystallization. You see, when a solution is supersaturated, it is unstable. It's like a tightly wound spring, waiting to release its stored energy. In the case of supersaturation, this energy is released through the formation of crystals. So how does this work? Well, the supersaturated solution is teetering on the edge of stability, searching for a way to return to its comfortable, stable state. And forming crystals is its ticket back to normalcy. As the solute begins to form crystals, it leaves the solution, reducing the level of supersaturation and allowing the solution to regain its equilibrium. In essence, Miers' theory of supersaturation provides us with the framework to understand how crystals are formed from a solution. It's the driving force for crystallization, pushing the solution out of its supersaturated state and into a stable one through the formation of crystals. So, supersaturation is the driving force for crystallization. But how does a crystal initiate its formation? Let's find out. The birth of a crystal. Sounds fascinating, right? And it truly is. The process of crystallization begins with a phenomenon known as nucleation. Picture it as a grand performance where nucleation is the opening act. It's the initial step that sets the stage for the magic of crystallization. So, what exactly is nucleation? Well, it's when a small group of ions, atoms, or molecules start to get organized. They begin to arrange themselves in a pattern characteristic of a crystalline solid, essentially acting like the blueprint of the soon-to-be crystal. This tiny, organized group forms a site upon which additional particles can be deposited. You could think of it as a seed from which the crystal grows. Now, it's not just about these particles coming together. The conditions need to be just right. The solution must be supersaturated, meaning it contains more solute particles than can be dissolved under normal circumstances. This supersaturation acts as a driving force, pushing the particles to arrange themselves into a more stable, organized form, the crystal. But it's not always easy for these particles to find each other and stick together. They need a helping hand, something to break the ice, so to speak. That's where nucleation comes in, providing a platform, a meeting place for these particles to come together and start forming a crystal. And once this nucleation site is established, the real show begins. The particles start to deposit on this site, following the pattern set by the initial group. Slowly but surely, the crystal begins to grow, layer by layer, in a process known as crystal growth. But remember, this is just the beginning. The birth of a crystal is a complex, intricate process that involves a lot more than just particles coming together. It's a dance of nature, a spectacle of chemistry that's as beautiful as the crystals themselves. Nucleation sets the stage for the next important step, crystal growth. After the birth comes the growth. Let's understand how a crystal matures. A crystal is more than just a beautiful object. It's a perfect example of nature's ability to create order from chaos, to form complex structures from simple components. So, how does a crystal grow from a mere speck to its final size? Well, the process of crystal growth is a fascinating journey that involves the addition of more atoms, ions, or polymer strings to the crystal that has already been nucleated. This is a delicate process where each additional particle must find its correct position in the crystal lattice. It's a bit like building a brick wall, where each brick must be placed exactly right for the wall to be stable and grow. But unlike a brick wall, a crystal is not built by human hands. It is built by nature, using the forces of attraction between atoms and ions. These forces guide each new particle to its correct position, allowing the crystal to grow in a highly ordered and precise manner. This process continues until the crystal reaches its final size, which can be as small as a grain of sand or as large as a mountain. But what determines the size of a crystal? Many factors come into play, including the concentration of particles in the solution, the temperature, and the presence of impurities. The higher the concentration and the lower the temperature, the larger the crystal can grow. Impurities, on the other hand, can disrupt the growth process and lead to smaller, less perfect crystals. With a well-grown crystal, we now need to classify and understand the different types of crystallizers. But that's a topic for the next scene, so stay tuned as we continue our journey into the fascinating world of crystals. Ever wondered about the different types of crystallizers used in industrial processes? Well, let's delve into the world of crystallizers, specifically tank and Swenson crystallizers. To start with, crystallizers are an integral part of industrial processes used to separate crystals from a saturated solution. They are broadly classified into two categories: tank crystallizers and Swenson crystallizers. However, let's not forget that there are more types too, such as the Oslo, draft tube baffle, vacuum, and the list goes on. Let's begin with the tank crystallizers. They are the simplest in design and function. Imagine a large tank where a solution is allowed to cool naturally. As the solution cools, crystals start to form. The slower the cooling process, the larger the crystals. This is why tank crystallizers are perfect for creating large, high-quality crystals, such as those used in the production of specialty chemicals and pharmaceuticals. Now, let's shift our focus to the Swenson crystallizers. These are a bit more complex than their tank counterparts. Named after its inventors, Swenson and Walker, this type of crystallizer consists of a shallow, open trough, equipped with a jacket for steam or cooling water, depending on the process. The solution is fed into one end and is slowly stirred as it moves towards the other end. This slow, gentle stirring allows for the formation of uniform crystals, which are then easily separated from the mother liquor. Swenson crystallizers are commonly used in the production of salts and sugars. It's interesting to note how these machines, as simple or complex as they may be, play a crucial role in various industries, turning saturated solutions into valuable crystals. So we now know about the different types of crystallizers. But what happens when things go wrong? In the world of crystals, not all processes go smoothly. Let's talk about caulking. This pesky phenomenon is like the proverbial wrench in the works for our crystallization process. Caulking is when our nascent crystals, instead of growing freely in the solution, decide to stick together, or to the walls of the crystallizer. It's a bit like trying to bake a cake, but instead of rising evenly, it clings to the sides of the pan, ruining your perfect dessert. Now, why does caulking happen? It's a result of unwanted interactions between the crystal surface and the surrounding environment. These interactions can cause the crystals to adhere to each other, or to the crystallizer's walls. But, like all challenges, caulking also offers an opportunity for innovation. Scientists continually devise methods to prevent caulking and improve the crystallization process. After all, understanding these challenges helps us to improve the crystallization process, and that's what science is all about.